Hello everybody, this is the first video of chapter 1, well first and only video of chapter 1 of the statistical learning course. So this chapter will consist in a brief introduction to the material covered in the entire class. So it's really a non-mathematical, very high-level conceptual introduction without going into deep details. So first I want to introduce two references that we shall be using for the course. These two references are two books that are available for free online legally. So the first book is An Introduction to Statistical Learning, and the second book is called The Elements of Statistical Learning. And you can go on these two websites to download the books for free. Okay, so you don't need to buy anything for this course. All the material is available online and on top of the slides and exercises I provide. So a substantial portion of the material covered during the course is drawn from these two books, and I'd say mainly the first one, The Introduction to Statistical Learning. At times I will use pictures from these books, so I will disclose when I do so, but please note that at some parts I'm relying on these pictures and I haven't done all of them myself. So as I said, some of the figures from the slides are taken directly from the Introduction to Statistical Learning with Applications in R textbook, so I want to acknowledge the authors of that book for such figures. Okay, so they said on their website that they give the permission to use these figures as long as they're properly cited, so this is what I'm doing here. So as I mentioned a bit earlier, the purpose of this chapter 1 is to discuss statistical learning. So first discuss why is it useful for, and second to have a kind of broad overview of classes of methods within statistical learning. Okay, so statistical learning is a broad topic which comprises several problems and several methods which attempt to solve them. So we shall discuss various ways to categorize such problems and the methods within the statistical learning literature. So I first wanted to start with a quote which is attributed to Yogi Berra. So sometimes the quotes attributed to Yogi Berra are not really from Yogi Berra, but they still are to, I guess, I don't know, to make them more famous. So the quote says, "It's tough to make predictions, especially about the future." Okay, so it's a bit funny because, of course, when you make predictions, it's always about the future. But why I put this quote here, it's because really the main objective of statistical learning is to be able to predict things that we don't know. So this chapter 1 from the slides covers portions of chapter 1 and 2 from the first textbook I present, Introduction to Statistical Learning, which shall be referred to as ISL onwards, and parts of chapter 1 and 2 from the ESL textbook, where ESL refers to the second book we mentioned earlier, which is Elements of Statistical Learning. Okay, so the vast majority of statistical learning tools are used to do one of the two following things. So first, the first objective of statistical learning, as I just mentioned earlier, is to make predictions. Okay, so there are quantities which are uncertain, or you can see them as random or unknown, and with the help of data, you want to be able to predict these unknown quantities based on the information you observe. Okay, so prediction is one of the main objectives of statistical learning methods. And a second objective is often to make what we call statistical inference. And what we mean by statistical inference is to try to assess the impact of one variable on another. So you want to know if one variable varies, how is it going to impact the other variable, so you can deduct either correlations or causal relationships between variables to understand how one impacts the other. So what we often want to do is the following problem. Let's say we have a random variable y, which is unknown, and we have observable random variables x1 until xp. Okay, so here these are the observables. This is y, which we don't observe. And the objective would be using these data, these observed data, we'd like to predict y. Okay, so for example, just giving one example that is discussed in the textbook, y could be the wage of a salaried male in North America, and the xi's could be the characteristics of the person, so its age, years of education, the current year, etc. Okay, so the idea is often we have a data set where both the y and the x's are observable. So we have a history of examples of a wage for a salaried male in North America, and here we have the history of characteristics. And then what we'd like to do is for a new person, so a new salaried male in North America, given its characteristics, then we'd like to make a prediction of what should be his wage. So we can see it that this example can highlight the two problems we mentioned before. So for example, we might be interested in predicting y given the x's in that problem, because let's say you're an employer, you'd like to know what's the proper wage to pay some person. So by running this analysis, then you want to predict the wage. So it's really, in that case, it's really a prediction problem where you'd like to know what's the should be the proper wage of that person that I should pay him to do the work for the company. But we can see that this problem can also be interesting from a statistical inference perspective, because if you're an economist, you'd like to know what are the main drivers of wages of people. Is it their age? Is it their years of education, etc.? And if you find, for example, that the number of years of education has a very high impact on wage, then you would write studies to encourage people studying longer to increase their wage, and etc. Okay, so this is an example of statistical inference where you try to deduct the impact of one variable on another variable. Okay, so here we're going to use some terminology. The variable y, which we're trying to predict, we often refer to it as either the dependent variable or the response variable. Whereas the variables x, so x is a multivariate, it's the set of all characteristics or all explanatory variables, we refer them as either independent variables, predictors, explanatory variables, covariates, features, etc. Okay, so all these 5 expressions I provided are names that are commonly used to describe the x's mentioned previously. Okay, so just to go back to inference, we said that inference is mainly a problem where we want to assess the impact of one variable on the other. Okay, so this problem often has the following associated questions. So first, in an inference problem, we want first to identify what predictors are associated with the response. So in many inference problems, you have many explanatory variables, but for most of them, they might have no or almost no relation with the variable being predicted. Okay, so One problem is to filter out all the predictors that are irrelevant and try to find the ones which have genuine interaction with the variable we're trying to predict. And once we know which variables are impactful, another problem consists in assessing the impact. Okay, so what's the relationship between the response and each predictor? So is it strong or small? Is it positively correlated, negatively correlated? Is it well summarized by a linear relationship, or the relationship is not linear, etc.? Is it a complicated relationship, simple relationship? Is there interaction between predictors, etc.? Okay, so statistical inference also asks the following questions. First, when you have a data set, what are the relevant variables within that data set? And for these relevant variables, can you characterize the shape of the relationship between the predictors and the response variable? So in problems that we will encounter, we have multiple types of variables, either for the response or explanatory variables. So sometimes the variable is a quantitative number. Okay, so a number in R, for example, a real number, the height of somebody, for example, if it's a predictor, the number of years of education that we mentioned earlier, etc. So many variables are numbers, um, which vary continuously. So these are quantitative numbers that are very common in problems that we described earlier. Sometimes you have other variables that are qualitative. Okay, so for example, one variable could be the country in which you live in. Well, countries are not numbers, so the variables are qualitative in that case. Or we have another more hybrid type of predictor, which is referred to as ordered categorical. Okay, so ordered categorical is kind of in between quantitative and qualitative. It's where you have, I'd say, qualitative uh, possible values, but the qualitative values have a logical order. So let's say you have small, medium, or large. Well, these are qualitative possible values, but there's some meaningful order. Okay, so medium is between small and large. Okay, so uh, these type of predictors or response variables can be often encountered in practice. Okay, so the various algorithms we will describe have to tackle are meant to tackle or to use different types of variables. So some methods that we will see can cope with any type of variable. Some, for example, if we take linear regression, you cannot. It's not as easy to use qualitative predictors than maybe some other methods we will see. Okay, so there's a way to do that. We will see that, but for some methods, it's more straightforward to use some types of variables than some others. Okay, a quick remark here. We said that we use the variable the letter capital Y to denote a response variable. So we will often use the following convention when the response is a number, so a quantitative variable. We're going to use Y for the response, but when the response is qualitative, we're going to often use capital G, where capital G means group. So group, the various groups are the various possible values for the qualitative random variable. Okay, so sometimes for the response we're going to use Y when it's a number, sometimes we're going to use G when it's a qualitative random variable. Okay, so we're going to see that um, the need to have both um, prediction ability and the ability to provide statistical inference by the methods leads to some form of conflict. Okay, so in statistics or in statistical learning, there's often a conflict between model accuracy and model interpretability. Okay, so when we design a prediction model, we want the predictions to be, of course, as accurate as possible. But sometimes, if we do statistical inference, we'd like to be the model to be easily interpretable, to be able to like deduct simple lessons provided by the models. Okay, but these enter into conflict because in some problems, to get accurate predictions, you need very complex models, very flexible models, but the complexity of the models make their interpretability much harder. Okay, it's much harder to interpret a complex model than a simple model. Okay, so uh, this is maybe one lesson. So we're going to see many techniques in the course, and there's no single one technique that is better in all cases than the other. So often the various techniques offer different trade-offs. Some are more complex, more accurate, but harder to interpret. So for example, if we have neural networks that we are all over the news nowadays, these are very complicated models that can be very accurate, but are sometimes very hard to interpret. Whereas conversely, if you use linear regression, your model might be less accurate if you have nonlinear relationship in reality, but it's simple to interpret. So if you want to obtain lessons from a regression analysis, then linear regression provides a straightforward story. Okay, so whenever we apply statistical learning and we have to choose the method which we're going to apply, we have to keep in mind that kind of conflict or trade-off where it's often impossible to have perfect accuracy and perfect interpretability. You have to choose or to accept compromising a bit of one to get more of the other. Okay, so the statistical learning models that we're going to see, well, at least in the earlier chapters, but let's say the first 2/3 of the class, they often assume a relationship between the response and explanatory variables. And this relationship, it's often characterized in the model by some function f. Okay, so for example, often if we have a quantitative response, people assume the following form. So it can often be assumed that the response variable is a function of the various predictors plus some noise term. Okay, so yi means the ith observation within your data. So you postulate that your ith observation is some function f of your p predictors. So xi1 until xip means the first, well, the p predictors associated to observation I, plus epsilon I, where here epsilon I refers to as a noise term or an error term with an expected value of 0. Okay, so for example, if you use linear regression, you have this relationship that is postulated where this f, it's simply a linear combination of the various predictors. Okay, but we can generalize this linear function to nonlinear functions, which we will do in some chapters of this course. So this is an example of quantitative relationship where y is a number. But if y is not a number, can you use a function f to characterize the relationship between the x's and the f and the y, sorry, and the answer is yes. So of course you cannot use this because if y is not a number, you cannot add a noise term which is a number. Okay, so how can you characterize the relationship between the response and predictors in a quantitative relationship? Well, one example would be the following, is to try to determine what is the probability of being in class G. So this is the value of the qualitative response given your predictors, and you can assume that this probability is some function f of the class, the probability of well, the class of which you're trying to assess the probability to be in, and your various predictors. Okay, so this would be an example of a relationship between predictors and the response when the response is qualitative. Okay, so a bit more terminology. Often in statistical learning, we hear about the words parametric versus non-parametric. Okay, so um, we said that often we assume the relationship between the covariates and the response is characterized by some function f. So statistical learning methods will typically aim at estimating that unknown function f. Okay, so basically we often assume some f exists to characterize a relationship, but we don't know that f, and we try to discover what that f is. So what's the difference between parametric and non-parametric model? For a parametric model, you assume that the function f has a very simple functional form based on some parameters. Okay, so for example, if you use that the function of parameters is a linear combination of the various predictors, where the coefficients of the linear combinations are parameters, then this is a parametric model, because you see that there are like a few parameters that enter into that relationship, and the problem of estimating f then boils down to estimate these parameters. Conversely, so you in a parametric model, you postulate the functional form for f, and based on some parameters, and then you have to estimate the parameters. Conversely, in non-parametric models, you don't really postulate a precise form for f. You try to let the algorithm learn the function f without imposing your prior belief on what f should be. Okay, so you don't say, let's say f should be a linear function or a quadratic function. You might simply postulate that it's a continuous function or something like that, and then you let the model try to figure out what that continuous function is. Okay, so still, okay, continuous is still an assumption, but it's much less precise assumption, and it's much more flexible than postulating a linear relationship, for example. Okay, so a parametric, you assume a simple functional form for f, and based on parameters, and you try to estimate these parameters. Non-parametric, you don't postulate a very specific form for f. You let the algorithm or your model learn the shape of f by itself. So how does it relate to the interpretability versus prediction accuracy trade-off that we mentioned earlier? Well, parametric models are often well suited for model interpretability, but sometimes a bit less for accuracy when you have complex relationships. So let's say you use linear regression. Let's use that as an example, or other simple parametric model. These are very easily interpretable because the shape postulated for f is often pretty simple, so you can have a clear view of what the impact of the predictors should be in that model. So for example, if you postulate linear regression, well, you assume that when you vary one of the predictors, the variation of the response will be linear. Okay, so you have a linear relationship. Okay, so but if you make an erroneous assumption about the functional form of the function f, then your model might not be accurate. Okay, so for example, if you apply linear regression, but you have a quadratic relationship between the response and the predictor, then your model will be wrong, so it will be less accurate. So conversely, non-parametric models are typically much more flexible, and can be better suited for prediction purposes, especially for if the relationships between the predictors and the response are very complicated. So if this relationship is complicated, parametric model might not do well, so non-parametric models might produce much more accurate results. But this additional flexibility might come at a cost. So the cost is that if you have a very flexible and complicated model which tries to learn f by itself, well, that complexity might lead the model to be harder to interpret. Okay, so if you calibrate a very complicated neural network to make some predictions, then it might not be as easily interpretable as some other simpler model. Okay, now we have to discuss what we call reducible versus irreducible error. So let's consider for the current discussion that the response variable will be quantitative, so a number, and we're going to use y. So the accuracy of a prediction y hat for an unknown, the unknown response y, will depend on two quantities called reducible error and irreducible error. So what do we mean by that? Let's assume the previous relationship. So let's go back here. Let's assume that we have this relationship between the response and the predictors. So the response is a function f of predictors, where we don't know that function f, plus a noise term. So the statistical model will come up with an estimate of the function f, which we shall denote f hat. And since f hat is not a perfect estimate of f, it will have errors. These imprecisions will create error. Okay, so the fact that f hat is not a perfect estimate of f is called the reducible error. So why is that? Why do we call it like this? It's because often we can come up with better estimates for f, better f hats, by either sometimes changing our model if the model is suitable. So this might improve f hat, or maybe having more observations to have better estimation procedures. So we see that by doing that, we can come up with better estimates f hat of f, and then make better predictions for our variables. However, let's say we had a perfect prediction for f. So let's say f hat is exactly equal to f, and we were able to make a perfect prediction of the function f. Our prediction model will still make some errors. Okay, because the response variable, it's not the function f of x itself, it's the function f of x plus epsilon, which is an error term. And this error term will lead to some errors. So even if you have the perfect prediction function f, so f hat is equal to f, you still have this remaining noise term, which will generate error in your prediction models. And this noise term entails that even if you have the perfect model, there's still a portion of error which you will not be able to fully remove from your model. So this is called the irreducible errors. Okay, so this is the error that cannot be reduced by improving the estimate of f. So in practice, why is the irreducible error larger than 0? Well, it's because epsilon typically contains variations in the predicted variable that are that is either unmeasured, so it's explained by variables that you just didn't measure, or cannot be measured because it's way too complicated. Okay, so the noise term contains effects that cannot or aren't measured because of too much complexity. Okay, so here when you have explanatory variables, sometimes explanatory variables can only explain so much. So if you only rely on these predictors, you'll make some error due to unperfect information that is not included in your predictor information provided by your current predictors. Okay, so let's illustrate that here. Let's assume that we have an estimate f hat and a set of predictors x. And let's assume just for this simple example that they are fixed. Okay, in practice we can treat these as random variables, but just for the sake of the explanation, let's say f hat and x are fixed, and then that you make the prediction y hat is f hat, your estimate of that function f, evaluated at your predictor. So in that case, the mean square error you make on your prediction is the following. So this is the expected value of the true response variable minus your estimate squared. So you can substitute y by f of x plus epsilon. So this is the functional form that was postulated early in the chapter, minus y hat, we assume that it's f hat of x. So here you can develop that square and have a first term, which is f minus f hat squared. So and now in this problem, this is deterministic because we assume f hat and x are fixed. Plus, now there's the cross term, twice times the expectation of epsilon times f of x minus f hat of x. And because we said the noise term has an expected value of 0 as per our assumptions, this term can simply vanish. And here, the last term, when we expand that squared, is the expectation of epsilon squared. And because epsilon has a 0 mean, this guy is the variance of epsilon. So we can see that we can decompose the mean square error of our predictions into a part that is reducible and a part that is irreducible. Okay, so the variance associated with the noise, regardless of what method you use or how precise your method is, you'll still make that error when you make predictions. Okay, this is something that you cannot predict the noise term. Conversely, if you want to work on better predictions, what you should try to achieve is to have estimates of the function f characterizing your relationship between your predictors and your response variable and the true function f here. Okay, so when you try to obtain better errors, what you're trying to do is to shrink the reducible error part by coming up with better models, better estimation, etc. Okay. Now let's discuss the difference between classification and regression problems. So we discussed earlier that many problems in statistical learning are prediction problems where we're trying to predict the response variable. When here a regression problem is when the response is numerical. So if y is a number, then trying to predict y is called a regression problem. Conversely, when y, the response, or sometimes we said we use the notation g, so here I've put y, but you could use g here. When the response is categorical or qualitative, then we say our prediction problem is a classification problem. Okay, so let's give an example here. If you're in an insurance company and you're trying to predict the expected number of accidents of a given driver in the next year that you insure, then you're predicted a number, okay, expected number of accidents. So this is a regression problem. Okay, you use the features of the driver to predict a number, the expected number of accidents. So this is a regression problem. Conversely, if you want to split the group of insured drivers into either bad drivers and good drivers based on their characteristics, then this is a classification problem because here the response y should be either good or bad. Okay, so y is not a number here, it's qualitative or or they're categorical in some circumstances. So this is referred to as a classification problem. Okay. Now there's also the supervised learning versus unsupervised learning terminology. So what's the difference between both? This is a very important thing to know if you do some machine learning. Supervised learning is when you train a model by providing the correct answer to your model during the training phase. Conversely, in unsupervised learning, you want the agent, which is learning, to learn by itself without providing him correct answers within the training phase of the model. Okay, so right now you see that, you say, well, this is a bit puzzling. So what's unsupervised learning if you just don't tell the algorithm what is good or bad? Well, the idea is unsupervised learning, what they're trying to do here is to find some underlying structure in the data that makes sense. Okay, so let's give a quick example to illustrate that point better. Okay, so for example, in linear regression, this is a supervised learning approach. Okay, so you have a clear response variable y in your data and clear predictors in your data, and in your data set you know the variable y and x, and you're trying to find the regression parameters beta, which provide the closest resemblance between your response variable in your data and your linear combination of predictors that you also have in your data. Okay, so in linear regression, you tell the learner what the correct answer is for all observations, and their correct answer is your response that you observe in your data set. Okay, so if you regress the height of some person based on, I don't know, its age or whatever, you can, in your data set, you have both the height and the age of many people. So because of that, then you can, you know what's the correct answer for each observation because you know the response. Conversely, if you have the following problem, you have a collection of DNAs of various animals, let's say, and you'd like to classify all these animals into various species based on their DNA. So you can see that in that case, there's no clear, good, objective answer. Okay, so what you're trying to do is to find clusters of animals that are similar together and that could be regrouped into some species. So there's no objective single good answer. What the algorithm will do in that case is to try to find some answer which does make sense. Okay, so there might be multiple ways to categorize animals into species, but you want the algorithm to provide at least a solution which makes sense, and to have in some way species where within a single species the animals are somewhat similar. Okay, so you can see that in the latter problem, you don't train the model, the algorithm or the agent by providing him the correct answer. You want to let the model try to figure out what would be one answer that makes sense by trying to find some suitable structure in the data. Okay, there's also the discussion about static versus dynamic models. So if you read about machine learning, sometimes they might use this terminology. So a static model is when you have a single data set that is fixed and that is not being updated through time. Okay, so in practice, sometimes you have a single data set and you want to make a statistical analysis on that precise data set. So then what you need is simply a static method where you make your observation and estimation and model calibration only once, and then you get answers from that. Conversely, you have dynamic learning methods where you have a data set that is constantly being augmented because new observations constantly flow through time. Okay, so for example, if you're a supply chain manager, you're trying to optimize your supply chain. Well, as time goes by, you have new and new observation that enter your your data set. So you want to refine your prediction models as soon as you get new observations. So then you need what we call a dynamic method, where the method needs to be quickly adapted by factoring out new information that is constantly arriving. Okay, so we many methods can have a static version or a dynamic version for estimation, but depending on what your objective is, will you apply the your method on a fixed data set or a dynamically uh, modified data set, then you might need different either techniques or estimation methods for these two distinct problems. Okay, so statistical learning, either primarily it's a statistics topic, or some might argue it overlaps with computer science. So it might be primarily a statistics slash mathematical slash computer science topic, but it has many applications in multiple fields. So for example, economics, finance, health science, biology, operations research, psychology, and this is only a, a subset of the various areas where you can apply this. So uh, statistical learning skills are highly valued nowadays by employers and academia, but not only in statistics or computer science, but in many areas. So the skills that I hope you will acquire during this class, they should be very helpful regardless of your area of application subsequently. Okay, so right now there's some form of hype about machine learning around the world, so it's a good thing for you to seize this opportunity to develop your skills within that class, that course, and then you can go on and apply what you've learned to either statistics or computer science directly, but other fields also, and what you will learn can be very relevant to this. So this concludes the lecture for the first chapter. Have a good day, and I'll see you next time for the second chapter.